Imagine a cosmic kitchen with a giant bowl ready. We have every ingredient known, all 118 chemical elements, from hydrogen, the lightest, to oganescent, the heaviest. What if we tossed them all in? Would it create a new universe or just a big mess? This is the ultimate thought experiment, a recipe for chaos or something new. Scientists love what-if questions. They push boundaries and help us understand the rules of chemistry. Elements are like tiny people, each with its own likes and dislikes. Some are friendly, eager to bond, while others prefer solitude. Mixing them all is like a huge, unruly party. What forces would take over? A gentle blend or a violent clash? The elements hold immense power, locked within their atomic hearts. Unleashing it all at once is a wild idea. Consider every possibility from a quiet fizzle to a star-like birth. Think of the variety: soft metals, gases lighter than air, rocks that form mountains, and radioactive elements. Each brings unique properties to this unprecedented elemental soup. The outcome is far from certain, but exploring it is a journey into the nature of matter and the forces that shape our world. Elements are the purest substances, chemistry's fundamental ingredients. Each element is unique, defined by its atomic number, which tells us the number of protons. Hydrogen has just one proton, making it element number 1. Gold, with 79 protons, is much heavier and rarer. Humans have known some elements since ancient times: gold, silver, copper, iron. These were easy to find and relatively pure in nature, prized by early civilizations. Other elements hid in compounds, taking centuries of science to isolate and name. Think of elements as letters in the alphabet of the universe. With these letters, all matter is written, from water molecules to complex DNA. Each element plays a special role. Some are common, like oxygen, while others, like astatine, are incredibly scarce. The story of elements is rich, full of strange discoveries and even stranger scientists. Alchemists dreamed of transmutation, turning lead into gold, laying groundwork for modern chemistry. They were the first true element hunters, chasing secrets held by matter. Their legacy lives on today, as we continue to explore the building blocks of the universe. The periodic table is a map of all the elements arranged by properties and atomic structure. Dmitri Mendeleev saw patterns others missed, leaving gaps for undiscovered elements. The table is a work of genius, with rows called periods and columns called groups. Elements in the same group often behave similarly. Group 1 holds the alkali metals: lithium, sodium, potassium, and friends. They are soft, silvery, and very reactive, eager to lose an electron. Imagine their role in our big mix. They wouldn't wait patiently. Then you have the halogens: fluorine, chlorine, bromine, iodine. They are hungry for electrons, wanting to gain just one. Fluorine is the most reactive, attacking almost anything it meets. Pairing an alkali metal with a halogen is a recipe for excitement. A quick, energetic chemical bond forms. Don't forget the noble gases: helium, neon, argon, and more. They sit on the far right, aloof and proud, with full outer electron shells. This makes them very stable, generally not reacting much. They are the snobs of the element world, or perhaps just very content. Their reluctance adds another twist to our grand elemental experiment. Toss all 118 elements together, and the first likely event is a massive explosion. Many elements are highly reactive, especially with each other. Cesium, an alkali metal, is intensely pyrophoric, igniting in air. Add fluorine, the most reactive, and an incredibly violent reaction occurs. This is just one pair among many. Hydrogen and oxygen form a famously explosive mix, needing only a spark. Sparks will fly from countless energetic reactions. Alkali metals like sodium would hit water or oxygen, creating intense heat and flames. This is chemistry unleashed, raw. Historically, humans learned this the hard way through experiments. Early gunpowder makers knew certain mixtures went bang loudly. Alfred Nobel's dynamite story is one of controlled explosions. But our mix has no control, it is pure elemental anarchy. The energy released would be vast, far beyond simple gunpowder's might. A sudden, fierce release creates a shockwave of immense force. Many elements are radioactive, adding more energy. The initial moments would be chaos, a blinding flash, a deafening roar, the birth of a new tiny star, perhaps for a fleeting moment. After the initial Big Bang, the temperature skyrockets. All those reactions are exothermic, releasing a lot of heat. We're talking thousands of degrees, hot enough to melt anything. Even elements with high melting points, like tungsten, would succumb. Imagine a glowing molten blob, a soup of liquefied elements. This is chemistry unleashed, raw. Historically, humans learned this the hard way through experiments. Early gunpowder makers knew certain mixtures went bang loudly. Alfred Nobel's dynamite story is one of controlled explosions. But our mix has no control, it is pure elemental anarchy. The energy released would be vast, far beyond simple gunpowder's might. A sudden, fierce release creates a shockwave of immense force. Many elements are radioactive, adding more energy. The initial moments would be chaos, a blinding flash, a deafening roar, the birth of a new tiny star, perhaps for a fleeting moment. Metals would melt and mix, forming strange new alloys. Non-metals might vaporize, becoming superheated gases. The state of matter would be extreme, more like a dense hot plasma. Some elements melt easily, like gallium and mercury. Even stubborn carbon, as diamond, would eventually burn or turn to gas. The pressures would be immense from expanding gases and reactions. Denser materials might sink, while lighter ones float. Convection currents would churn, stirred by ongoing reactions and heat. A dynamic inferno, constantly changing, ever shifting. A far cry from separate elements, now a single, raging entity, if only for a short, dramatic while. Amidst the heat and chaos, elements are forced together, forming chemical compounds. Metals bond with non-metals, forming salts, oxides, and sulfides. These are common stable compounds like sodium chloride and iron oxide. But could anything truly new form, something never seen before? Under extreme conditions, exotic molecules or unusual crystal structures might emerge. Scientists create new materials in labs under controlled extremes. Our elemental mix is uncontrolled, but the extremes are there. Most likely the end result would be a jumbled mess. A slag of stable compounds with the most reactive elements used up. Some strange alloys might form, mixtures of different metals with unique properties. Intermetallic compounds are possible, with specific ratios of elements. The intense conditions could force elements into unusual partnerships, even if only for a short time, before they break down or settle into something familiar. Elements sometimes surprise us, defying our understanding of rules. Consider xenon, a noble gas once believed to be inert. In 1962, Neil Bartlett made xenon compounds, shocking the chemical world. Our megamix provides extreme conditions with pressure and temperature. Could even helium be forced to form fleeting bonds? It's unlikely, but fun to ponder. Gallium melts at body temperature, turning to liquid metal in your hand. Imagine its fate in our hot mix. Mercury, a liquid metal, forms amalgams with other metals. In our elemental soup it would vaporize, adding its unique character. Its interactions are complex, even in normal settings. Phosphorus comes in different forms. White ignites in air, red is safer. What form would it take here in searing heat and pressure? Elements can be versatile, their personalities shifting with conditions. This mix tests all their limits truly, all at once. Surprising interactions could occur, revealing new insights. The experiment challenges our understanding of elemental behavior, a testament to the unpredictable nature of chemistry. Noble gases like helium, neon, argon, krypton, xenon, and radon are known for their lack of reactivity. Their full electron shells give stability, making them mostly inert. In our chaotic elemental mixture, would they remain aloof? Xenon, krypton, and radon form compounds under harsh conditions. Fluorine and oxygen are good partners, forcing these gases to bond. Our mix has plenty of fluorine and extreme conditions, so some noble gas compounds would likely form. Helium and neon are tougher chemically, extremely unreactive. Compounds of helium are theoretical, existing under bizarre conditions. Our elemental soup is hot, but perhaps not star-hot for long. Helium and neon might escape, largely unscathed by chemical bonds. They would exist as gases, floating above the denser mess. Observers to the elemental drama, a testament to their stability. After the fireworks and meltdown, what remains of our grand mix? Likely a chaotic scene, a heterogeneous collection of substances. Not a single uniform substance, but many different ones jumbled together. The most reactive elements form stable compounds like oxides and halides. Nature prefers low-energy states, so much of the mix becomes rock and alloys. A complex, unrefined ore body created in a violent instant. Gases that did not react form an atmosphere above the cooling mass. Not breathable air, but an atmosphere nonetheless. Ultimately, mixing all elements does not create a new universe. It mostly creates a hot mess that cools into stable things we know. Chemistry seeks stability, always. The journey is wild, but the destination is familiar, a reminder of simplicity's power in the face of complexity.